So next up, I'd like to work through example 16.3 in the textbook. So this problem is to maximize 7x1 plus 6x2 subject to these inequality constraints. And again, x1 and x2 are both positive, or non-negative. So this example I want to do with the tableau method, which is really the same thing as before, but it just saves on some computational costs. So if we want to use either version of the simplex method, the first thing we need to do is write our linear program in standard form. So instead of maximizing, let's convert that into minimizing. So we want to minimize negative 7x1 minus 6x2. Our inequality constraints we want to turn into equality constraints. So we're going to add slack variables x3 and x4. So this becomes 2x1 plus x2 plus x3 equals 3. Our next inequality becomes x1 plus 4x2 plus x4 equals 4. And our slack variables x3 and x4 should both be non-negative. So this is our new linear program in standard form. We want to minimize negative 7x1 minus 6x2, subject to these two equality constraints, and also subject to x1, x2, x3, x4 being non-negative. Okay, so like before, we write out our matrix. So our first equality constraint is 2x1, 1x2, 1x3, no x4. Our second equality constraint is 1x1, 4x2, 0x3, and 1x4. First equation is supposed to equal 3. Second one's supposed to equal 4. And then what we do is we're going to write down a negative 7 in the first spot and a negative 6 in the second spot, and then zeros across the rest of the row. So what I did here is I saw that we looked for the identity matrix inside of our table. If the identity matrix doesn't show up, we have to do something a little bit different. But for now, if the identity matrix shows up, put zeros under the columns corresponding to the identity rows, or the identity matrix. And then our objective function was negative 7x1 minus 6x2. So I put a negative 7 under x1 and a negative 6 under x2. Right, so it's important that our tableau was in this standard form where we had an identity matrix somewhere. If we didn't have an identity matrix, we'd have to do row operations to make an identity matrix. Okay, so this is the first step of doing this with the tableau method. And the point of doing it this way is that these numbers along the bottom rows are just the reduced costs. So right off the bat, we see that the reduced cost associated to bringing column 1 into the basis is negative 7. The reduced cost for column 2 is negative 6. The reduced costs for the columns that are already in the basis is 0. And then this number down here is going to be the negative of the objective function. Right, and we said these are the reduced costs. Right, and we can also read off the basic feasible solution from this table, just like before. So the associated basic feasible solution is going to have 0 entries in the rows that aren't in the basis. And then for the rows that are in the basis, we can just read down the column. So 3, 4. So that's our basic feasible solution associated to this tableau. Okay. So now that we have the reduced costs sitting below the tableau, we can just figure out immediately which column we want to use. So we bring column 1 into the basis. Since -7 is the smallest entry in the bottom row. And when I say it's the smallest entry in the bottom row, I just mean among these 4 elements. I'm not including the bottom right-hand corner. Okay, so the next thing we need to figure out is which column enters, or which column leaves the basis. So the way we figure that out is we compute, well, 3 divided by 2 and 4 divided by 1. So I looked at the rightmost column. Rightmost column was 3, 4. We said we were going to bring the first column into the basis. So I take 3 divided by the first guy in the first column, and then I took 4 divided by the second guy in the first column. All right, so I compute 3 divided by 2 and 4 divided by 1. Now, which one is smaller? 3 divided by 2 is smaller. So 3 over 2 is smaller. So the column corresponding, well, the column corresponding to 3 for our basic feasible solution will leave the basis. Right, so if we look at our basic feasible solution over here, 3 was in the third column. That was the guy corresponding to this 3 up here. And so it's the third column that's going to leave the basic feasible solution, or going to leave the basis. Okay. So which entry are we going to pivot around? Well, we're going to look at the first column, because that's going to enter the basis. And then we said the one that's going to leave the basis is the column corresponding to 1, 0. So 1 is in the first row of the matrix, so our pivot is going to be in the first row. So we're going to pivot about the 1, 1 entry of the matrix. So when we do our pivot, our goal is to make the first column look like 1, 0, 0. So to make that happen, I'm going to divide the first row of the matrix by 2. And then I'm going to use that row to zero out all of the other entries in the first column. So if I divide the first row by 2, I get 1, a half, 0, 3 halves. Right. Now to zero out the second entry in the first column, I'm going to subtract this row from the second row. So I'm going to take 1 minus 1, that's 0. 4 minus a half is 7 halves. 0 minus a half is -1 half. And 1 minus 0 is 1. And 4 minus 3 halves is 5 halves. All right, so I divided the first row by 2, and then I subtracted the first row from the second row. In order to zero out the last row, what I want to do is add 7 copies of this first row to the last row. So if I do that, 1 times 7 plus negative 7 is 0. That's why I chose 7 copies of the first row. Take a half times 7 and add it to negative 6. That gets us negative 5 halves. And we continue doing this. We get 7 halves, 0, and 21 halves. Okay. So now our associated basic feasible solution, let's just write it down to sort of see what's going on. Well, we're going to have 3 halves now in the first coordinate. The next 2 rows, or the next 2 columns, are not in the basis. Third column is in the basis. It's the 5 halves. Right. So this is our new basic feasible solution. Now, what's great about this method is that we update the reduced costs as we go. So we see that there's 2 reduced costs. There's negative 5 halves and 7 halves. Well, 7 halves is positive, so we're not going to use 7 halves. The only column that we can add to the basis to reduce the cost is the one associated to negative 5 halves. So we're going to use the second column. So next we compute 3 halves divided by 1 half and 5 halves divided by 7 halves. So what are we actually doing in this step? We're looking down the column that we chose. And compute the ratios, or let's say divide by the entries in the last column. But we only want to look at the positive entries in the column. So here, we chose the negative 5 halves column. That had entries of 1 half and 7 halves. Both of those were positive, so we want to compute both of those quotients. So we only want to look at the positive guys in that column. So in this case, both of the entries are positive, so we use both of them. If we had like a negative 7 halves here, then I would only compute 1 half divided by 3 halves. I wouldn't do the negative 7 halves divided by 5 halves. So all of these values that you get should be positive. These correspond to how much you're able to move in the direction associated to the step that we're taking before one of the entries becomes 0. So if one of those guys was negative, you'd actually be able to move infinitely far before the corresponding entry became negative. So this could go wrong. It could be the case that all entries in that column could be negative. Then the solution is unbounded, or then the problem is unbounded. Meaning we can make the objective as small as we want. Okay, so in our case, none of those entries were negative, but it's worth pointing out that if one of those entries is negative, then you skip this step for that entry. So in our case, we do 3 halves divided by 1 half, that's 3. 5 halves divided by 7 halves, that's 5 sevenths. So 5 sevenths is smaller. So that means we're going to look at the second row. All right, so we're going to pivot about the 7 halves element. All right, if we do this pivot step, we want to multiply the second row by 2 sevenths, and then we want to clear out the second column. So second row is going to become 0, 1, negative 1 seventh, 2 sevenths, 5 sevenths. Right, and then I want to subtract half of the second row that's now normalized from the first row. So if I do that, I get 1, 0, 4 sevenths, negative 1 seventh, and 8 sevenths. And then if I similarly zero out the entry in the bottom row, I get 0, 0, 22 sevenths, 5 sevenths, and I believe 86 sevenths, assuming my notes are correct. All right, so now we look at our bottom row. Our reduced costs are 22 sevenths and 5 sevenths. So our reduced costs are both positive. Or I should say all non-negative. Therefore, we found an optimal solution. Right, so our solution is that x1 is 8 sevenths and x2 is 5 sevenths, because the basic feasible solution associated to this tableau is 8 sevenths, 5 sevenths, 0, 0. Right. So if we go back to our original problem, well, our modified problem, we were minimizing the negative of the original objective. So remember this quantity in the bottom right-hand side, that's the negative of the objective. So negative 86 sevenths is the optimal value of the objective. For the linear programming standard form. and therefore 86 sevenths is the optimal value for the original problem. Right, and 86 sevenths was achieved when x1 was 8 sevenths and x2 was 5 sevenths.